First thing that you should end up being familiar with is this kind of overall summary of your bonds versus your forces. Students that have had me should recognize this, kind of the application behind it. What we're looking at is the interplay between our bonds and forces. Meaning that if we have a polar covalent bond, we can start to predict something about the intermolecular forces that that molecule will exhibit. Okay, it matches the color wheel. So if I have a green polar covalent bond, I expect a green type of force, which puts me as the dipole-dipole or hydrogen bonding forces. Why does that become important? What happens as we go from black to red in the forces? We get a stronger force. We want to avoid the idea of bonds in that circumstance. But the strength of our interaction increases. So there's a stronger attractive force between our atoms as we move from a London dispersion up to an ionic force. That plays its role when we look at physical properties, melting points and boiling points. It's a common question to pop up on the ACS test, particularly centered around alcohols, or around oxygens primarily. Oxygens are kind of nice because they give us hydrogen bonding. So we've got an extra kind of strong intermolecular force. It's one of the forces that's primarily involved in all life as we know it through water. So it's incredibly important. That force is so much stronger that if we see a molecule with that intermolecular force, we typically see that compound be in what phase? I give you a compound with hydrogen bonding within that compound. What phase would I expect for that compound? Okay, either a liquid or a solid phase, because they have stronger forces. We would not expect them in the gas phase, okay, at least not easily. So we're trying to use those forces to imply something about melting points and boiling points. There's a few alcohols kind of scattered around. We've got, what is that? Sec-butanol in the upper left-hand corner, just as a generic alcohol. We've got a phenol in the upper right-hand corner, which we'll talk about. What's special about phenols? Are they really alcohols? They are so reactive as alcohols that we give them a different name. We call them phenols. So an alcohol is typically just an OH bound to a carbon. Well, in a phenol, we have the OH, and we have it bound to a carbon, but that carbon happens to be part of an aromatic ring, which then changes the chemistry of the oxygen-hydrogen bond. Because that chemistry changes significantly, we end up calling them phenols as opposed to alcohols. Two more fun random examples at the bottom. You've got capsaicin as a phenol, and then you've got geranol as an alcohol. Okay. So nice scents that we could play around with, or just hot, spicy things. General summary of our functional groups so far to date. Notice the alkynes are left off. Our alcohols are a bit problematic, and this is where I would kind of run into the issue with organization of this. We have an electrophilic carbon, we have a nucleophilic oxygen, we have a Bronsted-Lowry basic oxygen, and we have an acidic hydrogen. So pretty much every possible reaction we could possibly think of, alcohols have some ability to play with. Right? Because they've got a lot of potential reactivity within each of those atoms. Right? That's what makes them trickier to deal with. So you've got to watch out for that. We've got a bunch of possible things that we can deal with when looking at our alcohols. Okay? In general, our melting points are higher because of that hydrogen bonding force. We're going to keep coming back. I've decided this is one of the best organizations I can come up with. I'm going to keep coming back to this slide and actually this next slide, synthesis and reactions. Okay, so when we look at the synthesis of alcohols, we're looking at how can we make this OH bond, okay, or this technically carbon OH bond. And we've got 4 separate categories in which we could drop it, okay, along with their overall reactions. We could go through and do a substitution reaction. That's ultimately a review of Chapter 7. Probably not going to talk a lot about that because it's a review of stuff from last semester. Okay? We've got a couple slides on it. What we're looking at doing is making the carbon-oxygen bond. Okay, so starting with a sigma structure. We can make it via an addition reaction, okay, via a reduction. That one's a little bit trickier. What we're doing in that case is reducing the amount of oxygen bonds. So if we're going to synthesize it, we're going to get rid of a pi bond. Okay, so we're doing an addition reaction around there. We could also do a different type of addition reaction. We can do an addition about our alkenes, which is our pi bond formed in that situation. Okay? So we're looking at putting on that OH in a variety of different ways. The last one is make via addition with a special reagent known as a Grignard reagent. That is actually focused back around that blue pi bond again. Okay? So let's take a look at some of these in a little bit of detail. What functional group are we looking at when we make via our substitution? Substitution, alkanes won't work because there's no functionality with our alkanes. Alkyl, halide. We need a leaving group, something to substitute for. Our additions, okay, via reduction. What type of functional group are we looking at? I know it's kind of tricky. It's starting with a carbonyl, okay, that blue pi bond. Our additions via well, there we go. We could look at an addition to an alkene. Okay, again, one of those ones that we probably won't spend a lot of time on because it's a officially review from first semester. Okay? And then the last one, that orange, is doing an addition reaction of a Grignard, again from a carbonyl. Okay, the carbonyl functionality. So what we're starting with is a variety of different functional groups. What can we do to those functional groups to change them into alcohols? So we're looking at the synthesis of our alcohols. How about our reactions of our alcohols? Okay, we just listed off all of our possibilities on this, and this is where our alcohols become obnoxious. We've got an acidic hydrogen off of that oxygen. How acidic is it? Is that really acidic? Weakly acidic? Not acidic? Hydrogen bound to oxygen. How acidic? Can I give you another example here? Instead of it making an alcohol, let's call that a hydrogen. How acidic is that compound? Not very acidic. What's the difference between carbon and hydrogen? Not much. What do we expect for the acidity of our alcohols? They are weak acids. Okay? They are not super strong acids. Okay? They do have some acidic characteristics to them, so we can pull that hydrogen off, but they aren't super strong acids. So we're looking at acidities about the same as water. Okay? And water, yes, has some acidic properties, but it's not that strong. It's kind of our neutral base area. Our alcohols sit right in that area.
Is that because of the fact that the oxygen kind of has a partial charge and hydrogen has a partial charge? So they're kind of...
It still goes back to those partial charges. Exactly right. The next issue we run into, our oxygen can act as a base. Why can the oxygen act as a base? Big hint. It has lone pair electrons. It has extra electrons. Those electrons it can donate to a hydrogen, making it act as a base. Right? Unfortunately, does it have to donate those electrons to a hydrogen? No, it could also donate those to something other than hydrogen, so our oxygen can also act as a nucleophile. So we're looking at a substitution reaction in that case. Okay. Last ones. We've got an electrophilic carbon. And that carbon at the bottom is electrophilic. Why is it electrophilic? oxygen is more electronegative than carbon, so it starts to suck that electron density away, making our carbon positive. So we have an electrophilic carbon, which means we have the potential for substitution. All right, the last one on there, acidic hydrogen. Didn't we just talk about an acidic hydrogen, though? Yeah, am I talking about the same one? Probably not. Good answer. What we're looking at with this last case is that that alcohol or that oxygen has drawn so much electron density away that it actually starts to affect atoms further away. That hydrogen can become slightly acidic, which means those electrons could swing in, kicking out our OH, doing an elimination reaction. Okay, so our alcohol has the ability to do this kind of long distance effect within our structure. We do have to have the proper conditions to allow for each of these situations to occur. And we don't just throw it in and say, oh, I want it to act as an acidic hydrogen, so now it's going to act as an acidic hydrogen. You have to evaluate the reagents that it's thrown in there with and decide, is that its best role? Is that what it's most likely to do? Okay, and that's where a lot of this will become challenged. Okay? So as we go through and look at each of the reactivities, what we'll do is start the discussion with one of these slides, either synthesis or reaction, and I will try and bold whichever topic we're looking at. So you can recognize where our functionality is going to occur or where our reactivity is going to occur. Before we do that, every functional group runs into nomenclature. So we already know my least favorite subject. This is a nice summary of everything on here. You'll notice that I didn't just give you or highlight our alcohols. I've also highlighted one other functional group. Why would I highlight ethers as well? So we've got an example of an alcohol now in the lower left-hand corner. If I asked you to draw an example of an ether in the lower right-hand corner, what is it? What was the difference between carbon and hydrogen? Very, very little. So the reactivity that we kind of expect for alcohols, a lot of it overlays very similarly with our reactivity of our ethers. Right? With some kind of caveats within that. But because the reactivity is similar, we typically group them in it as well, which means you also need to know how to name your ethers. Okay? Primary ways to name your alcohols. Alcohols are very high up in the priority list, which means we change the ending of our name to the OL ending. Right? If it's an ether, ethers are very, very low in the priority list. And I know that doesn't really seem to make much sense, but we'll look at an example here in a second. We'll look at these substituents attached to the oxygen. We'll name each of those substituents, and then we'll call it an ether. Right? Classic example. What ether do you work with in the lab so frequently? Diethyl ether. Di meaning two, so we can change that name to ethyl ether. What does that mean? Take an oxygen and put on either side of it ethyls. There's the name diethyl ether. Okay? Really just comes down to practice. I think I've got some practice already up there for the alcohols. I am working on getting some other alcohol homework up there. So naming and referencing. First we'll deal with the referencing there. When we looked at primary, secondary, and tertiary, it was looking at how many carbons were attached, which works great when we looked at carbocations or alkyl halides. But we do run into an issue with alcohols. How many carbons are attached to an alcohol? One. Only one. Never more than one. So how can we get primary, secondary, tertiary?
What is that carbon attached?
What we're looking at is the carbon to which the alcohol is attached. How many carbons are attached to it? Okay, so we're stepping one atom a little bit further away to get a better reference on what's happening around it. So our primary, we're concerned at looking at, the carbon to which our alcohol is attached only has one carbon group, primary. Carbon to which our alcohol is attached has two carbon groups, secondary. Okay? With nomenclature, I'll give you a a minute, starting now, to deal with the nomenclature of these two compounds. Yes, they are both difficult in their own way. This one's probably a little bit easier. I hate nomenclature, so hopefully I get this right. A couple ways that we can go through and address this. The first thing to do is going to be to circle the main chain. Whoops. And that would be wrong. Sort of. Okay, well, what I'm actually going to do is actually circle in that OH as well as part of this. Because we can go primary, secondary, tertiary alcohols, we don't really care where the alcohol shows up within our longest chain, as long as it's part of our longest chain. Okay? That means I will include the carbon out here as part of my longest chain. Does that kind of make sense? Why did I not circle this carbon as part of the longest chain? The alkene has a higher priority than the alkanes, so I'll name that as a substituent. So we've got 1, 2, 3 substituents that we can name on this. What is the length of my chain? So we're looking at hept. Okay, I hear an N. Why do we have to do N? Because it's an alkene, not an alkane. And all for the alcohol. I heard some people just say heptenol. Technically wrong. You need to specify where the alkene showed up and where the alcohol showed up. People say, well, I just include that number in front. What does the 2 refer to? Is it obvious in the way I've numbered it? No. We need to make sure that it is absolutely obvious where our functional groups show up. Okay? Sorry, I need more space. And yeah, we would need all these stupid dashes in it as well. Okay? So now where do those functional groups show up? Depending on how we number this, we end up with different numbers. We number right to left, so that would be 2, 6. If we numbered left to right, it would be 2, 6. If we numbered right to left, it would be 1, 6. So what's our answer? 2, 6 or 1, 6? Why 2, 6? Alcohol has the highest priority. We must number it first. So our alcohol shows up at 2, the alkene shows up at 6. We've got other substituents that we can then tag in here. Those substituents happen to be methyl groups. There's 3 of them. Where are those 3 located? 5, 5, and 6. Number each and every single one. Yes?
Could it be 6 heptene, 2 all?
On where you drop that number, I would say no in that case, but I'm not positive. You're definitely running into a gray area for me. When you've got 2 functional groups fighting for the suffix, the ending of the name, specify the number right next to it. Okay. I think you are still okay with that, but try and get your number as close to where you specify the functional group as possible. How do we kind of get around this? You will only see multiple choice when it comes to these. I will not expect you to go through and come up with these full names. Because if you put a space in there, wrong. Put the dash in the wrong space, wrong. Forget a comma, wrong. Spelled hept without the H, wrong. Okay, there's too many different ways that it can go wrong to deal with the nomenclature there. You guys okay with nomenclature? Do I need to do the other one? We'll attempt this really quickly. Oh, this one's ugly. This one's really, really ugly. That's going to be your main chain. We'll include the alcohol in that main chain. Okay, so this one's bent. Why is this one going to get particularly ugly? There's not only well, it's almost two sites of stereochemistry. We have stereochemistry about where our alcohol is located and where the chlorine and bromine are. So we have to specify R and S for both those positions. But we also have an alkene with cis-trans isomerism. So we have to specify an EZ and multiple R and S's in this. Okay, I really don't want to name this one. I should have thought better of this. Okay. I will figure out what the name is for that in lab and then tell you guys later. How about naming ethers? You want to do practice on that one? Okay, yeah, so let's do the far right one. Again, I'll give you a minute. Once we know what our substituents are, we just put our name together and we end up with methyl tert-butyl ether, also known as MTBE, commonly found gasoline. MTBE, bleh. That's all, folks. MTBE is found within gasolines. I think they might have stopped putting it in there. I don't remember.
The methyl goes first.
That was going to be the part that I'm not positive on. I know it's MTBE, which means methyl needs to go first. Why should the methyl go first? That's the thing that doesn't make sense to me. Okay, so I know it's MTBE, but I don't know why. This then means that the tert takes priority, which doesn't really make sense to me because every time we've dealt with those precursors, the tert doesn't show up first. Okay, so I'm not sure why we put it with the methyl first. I just know in this case we do. Okay, so remember, when it comes to nomenclature, you have to know the rules. It's really just opening up the textbook and looking up the rule. Every time it comes to a nomenclature question, that's what I do. I open up the textbook, what's the stupid rule? There's the rule, okay, now I'm done. Okay? So use your textbook to find those rules. What I've given you on that previous slide, wherever it was, is kind of an overview summary of all of those pieces. This should get you through the bulk of your questions, but not through all of them. Whoops. So here's our whirlwind roll through our synthesis of alcohols, our substitution. So this is ultimately our chapter 7, okay, which goes all the way back to our different types of mechanisms, both our SN1 and our SN2. So if we take a look at this alcohol, we need to supply the oxygen and our hydrogen. Okay, as what class is that going to be supplied as? Okay, so is our oxygen being supplied as a Bronsted-Lowry acid? Is it being supplied as a Bronsted-Lowry base? How is that oxygen being supplied to this reaction? I know, blank stares. Okay, I'll accept that. Let's take it a step further back. What we're looking at is the synthesis of this bond, that oxygen-carbon bond. Okay? Where do those electrons likely spend most of their time? Why on the oxygen? It's more electronegative, so it wants them more, which means the oxygen comes in with what charge? Very large partial negative, and our carbon comes in as a partial positive. So our oxygen most likely acts as what in the course of this reaction? Electron donor or electron acceptor? An electron donor, which means it is best supplied as a nucleophile. Our carbon is acting as an electrophile. Okay. The next part is what functional group, what starting material could we use to supply these things? Let's start with the carbon. I want that carbon to be positive. How can it be positive? What does it need to be attached to? Something electronegative, drawing electron density away. Ideally, whatever that something is doesn't have any other chemistry associated with it. It's just electronegative. Do we have an element that is electronegative that is only allowed one bond? Yeah, all of our halogens. What we're looking at for our carbon substrate is probably an alkyl halide as a starting material. Okay? So break it down into the pieces and start to then add stuff in as you see fit. So we're looking at some kind of Rx. Okay, now the question is, how do we supply the oxygen? This is where it gets tricky. Said it needs to be supplied as a nucleophile. Do we say anything about strong or weak nucleophiles? No. So it could be a strong nucleophile, it could be a weak nucleophile. What's a good weak nucleophile that can supply OH? H2O. What if we want it to be a strong nucleophile? Now it needs to be a negative oxygen. We'll go in with our OH minus or NaOH. Is that going to change the mechanism by which we run the reaction? Absolutely. Okay. OH minus is a strong nucleophile, which suggests that we run under SN2 conditions. H2O is a weak nucleophile, which would suggest we run under SN1 conditions. How do we know which reagent we should be supplying? You have to go back to the other components of substitution. There's 4 things: substrate, leaving group ability, nucleophile, and your solvent. Right, well, solvent we can almost always toss out the window. Unless we're directly asking about solvent, it's not worth looking at. Leaving group is the same in both cases. We're changing the nucleophile, so that doesn't count. Only one thing is left with which we have to look at to try and decide which mechanism, and that is the substrate. Right? So we would have to look to see what that R specifically implies. So let's look at an example. Let's say that we're starting with this substrate. I don't know why I did X. Actually, I do know why I did X. Just make that a bromine. What starting material or what reagent should I add to get this reaction to work? Just gave you 2 options, 50-50. Okay. Substrate is going to determine what's happening here. What type of substrate do we have? We have a tertiary substrate, which favors which mechanism? SN1, which means which nucleophile do I want to add? H2O. If we add the OH minus, does this reaction work? So now let's change it around. We add OH minus, now predict the product. For it to run substitution, we would expect a primary substrate because we've got a strong nucleophile. So SN2 doesn't work. What ends up happening is we run an elimination. Okay? So it's knowing the balance of what happens when you change those substrates. How do you know that? You have to be super familiar with all of the components. Come on. Oh, we just talked about all of that. All of these components. What makes up the substitution reaction? What favors SN1? What favors SN2? How do these things dynamically interact with each other? What happens if you change one? It shifts to a different mechanism. Okay? As far as deciding, even as we went back and took a look at, and we'll look at this question in just a second. Looking at this one, and I said, okay, what happens when we go through and switch in OH minus? You'll notice that one of the first things I did was erase the product. Okay, why would I erase the product? Because if we draw it out like this, what do you think? Oh, well, OH minus just substitutes in it. It works perfectly.
No.
Okay? You don't see that you now have to predict the product. And if we go through and erase the product, it's now an entirely different question. You aren't looking at an answer. You're looking at how do I get to that answer. You must write it out. Okay? So if you're going to come up with a hypothetical question, which is fine, by the way, people ask me hypotheticals all the time. Generally, let me finish one question before you throw me a hypothetical, and then we can switch to the hypothetical, just for future reference. Okay? When you go to a hypothetical question, make your hypothetical question out, set everything up so that you can then evaluate it. Don't start trying to crank through it in your head, because you'll make the simple mistake of just saying, oh, it just looks like a substitution reaction. It looks like a substitution reaction because you drew it as a substitution reaction. Get rid of that product and reevaluate what you think should actually happen. Okay? So, let's look at a couple questions here. So, let's try and synthesize these. Give you again another minute here to evaluate. Okay, so let's start with the bottom one first. We're trying to make that alcohol. So if we go backwards, we're going to cleave that. We're going to have our CH3, CH2, then bound to something with some kind of OH supply. Okay, good leaving group. There's our bromine. Now do I add it as HOH or water, or do I add it as OH minus? How do I decide? Look at the substrate. The substrate is primary. Okay. Under primary conditions, what do I want for my nucleophile? It needs to be strong, which means I need to add OH minus. Would I get an elimination? Not very likely, because under the E2 conditions, which is what this would push, E2 favors substituted alkyl halides. This isn't a substituted alkyl halide, it's primary. Okay? So this would almost give us perfect yield. What's the issue with the question above? We again now have the formation of our alcohol, if you will, but the question becomes is which side is our alcohol bond? Okay, because I put carbons on either side instead of that hydrogen. Well, if you don't know, draw them both. So let's color code. If I was going to make the purple one, plus what? H2O won't work because I need a CH3. So I could add the HOCH3. I don't want OCH3 minus because substrate is tertiary. I need to go under SN1 conditions. What if I broke the other bond? I already forgot what I was doing. Oh, BR. And do I want my nucleophile strong or weak? Take a look at the substrate. Substrate is zeroary, which is effectively the same as our primary, which means we want a strong nucleophile. Two possible answers. Guess what? One of them is correct. You want a hint? This species needs to act as what? A nucleophile. What's our characteristics of our nucleophiles? Negative. This is negative, so that tips up. What else? Small. This is wicked bulky. This species would react preferentially as a base, not as a nucleophile. We're going to expect a very low yield in that situation. Okay. There isn't anything really remotely acidic for it to react with, so it would probably still work. But the easy fix as far as an exam question would be, let's just make this a CH2, CH3. You just add that extra carbon. Now I do have something that's acidic. Under that second reaction, I would expect the elimination, not the substitution. Okay? Only the top one gives me the substitution. The bottom one gives me the elimination product. That was a goofy looking E. Questions? So we're starting to run into being very careful with what we choose for our reagents. And then once we've taken a guess, check. Erase the answer that you were trying to solve for initially, and just take a look at what you provided as an answer and evaluate how do these reagents stack up? Which mechanism or what reaction would I expect to come out of this? Right? Is it tricky? Yes, but if you write it out, it will help you get through it. So our defining terms, this is just review information from our substitution chapter. Those are our 4 primary sections. What we would then do is break that down into each of the individual mechanisms. You've got your SN1 mechanism, which happens officially in 2 steps. Depending on the substrate used, you might see it in 3 steps because we have to pull off a hydrogen, right, to get it into its neutral state. SN2 happens in 1 step. We go through that nice little intermediate. You can see a summary of your rate laws on this as well. Right, so you just have to be aware of how everything processes. Again, now put in another format, nice big substitution review overall on what you would expect for your substrate, what you expect for your nucleophile, leaving group, substrate patterns, solvents, secondary effects, stereochemistry, rate laws, all that fun stuff. Okay? Question that I've seen pop up a couple times on the ACS tests is stuff about rates. Okay? Because classically, students hate rates, nobody looks at them. Okay? But they're there. They explain what happened with the mechanism. So they can go through and ask you a question about rate. If you don't know what's going on with the mechanism, you can't answer the question unless you've memorized the rate. Okay? Whirlwind review, that was all first semester. Questions on substitution before we actually move into the real new stuff? It wasn't too bad. I was hoping to do those slides in 10 minutes. Only took me 30. Sorry. Synthesis of alcohols. We'll look at the reductions. So this goes into chapter 9, I believe it is. No. Chapter 12. So it's the second half of chapter 12 for our redox reactions. What we're going to look at is how can we make the alcohol via a reduction reaction. What we're implying is that we are going to start with a pi bond between our carbon and oxygen, and we're going to turn that pi bond into hydrogens. We're going to make our alcohol. Before we even get into those, general review, how would you decide the oxidation state for, say, sulfur in this? What do you guys go through and do? Wow, that long ago. Really? No ideas? What's that? Oxidation state on the hydrogen. Let's try that. Anybody know the oxidation state for hydrogen? It's +1. So we could go through and look at our oxidation states of each of our atoms. Sulfur we don't know, so let's just call it S. Do we know the oxidation state for oxygen? -2, good. We're starting to wake up. I like it. Okay. So that means sulfur must be a +1, right?
Don't you feel like taking into account for us?
We have to take into account how many of each of those are present. There are 2 hydrogens present. How many sulfurs are present? 1. It's okay, common mistake. How many oxygens? 4. What's our overall charge on this molecule?
0.
How do you know it's 0? Upper right-hand corner, there's nothing written, which means the charge is 0. Now you could go through and solve for sulfur, and we get 6. Thank you. Sulfur is +6. Okay? So a new question. What are the oxidation states for carbon? Okay? These you might actually be able to do because our carbon is actually the central atom in all of these cases, so it's not too bad. But what if I went through and drew on another carbon? What's the oxidation state now for that carbon? So we look at a much larger structure that we're typically dealing with in organic chemistry. We don't have a central atom to which everything is attached, and we can assign our oxidation states around. It becomes a little bit trickier to deal with. Okay? A few different methods to go through and do this. I don't remember what your textbook suggests, but the way I've gone through and done it before is homolytically cleave. So do a homolytic cleavage of electrons minus the heterolytic. Equals your oxidation state for the atom. Everybody understands what that means, right? If there's no no's, then I guess you do know what that means.
Heteroatoms are oxygens.
Heteroatoms are oxygens, but that does not mean heterolytic. So what we'll do is look at each of our bonds. Janine had the right idea. We got 2 electrons in each of those bonds. We'll go through and do the homolytic cleavage first, meaning we split each of those bonds so the electron goes back to its parent atom. So in that first case, our homolytic cleavage is 4 electrons around carbon, minus the heterolytic cleavage. Now we go based on electronegativities. This is where we do run into some gray areas with carbons and hydrogens. Which is more electronegative, carbon or hydrogen? Carbon is slightly more electronegative. So when we go based off of our heterolytic cleavage, what happens? Carbon takes all of the electrons, and its total count is 8. So its oxidation state is a -4. Let's go to the complete opposite spectrum. What happens in this case? Our homolytic cleavage, carbon again, 4, minus heterolytic. Oxygens take all of the electrons, which means carbon has 0, which means our oxidation state is +4. So when we look at this spectrum, which number is smallest? -4 or +4? -4. Which number is the most reduced? What's the smallest number? I know, it's definitely a bad English thing, but it's the best thing we can do. -4, which means what we're looking at in our first case is our carbon is fully reduced. We cannot reduce any further. In our last case, what's happened? Carbon has lost all of its possible electrons. It is fully oxidized. You should be able to go through based on these little rules and come up with the oxidation states for the carbons in each of those intermediate structures. Okay? Yippee, have fun with it. Other way you can do it is look at your reaction, which is really ultimately what we're concerned about. For an individual reaction, was our carbon reduced or oxidized? If we look at individual oxidation states, we'd have to do that for both our reactants and our products. That can get a bit tedious. So if we look across the reaction and look for what changed, we can try and decide. So this alternate method, a reduction is increasing the amount of hydrogens. We looked at our methane, maxed number of hydrogens, fully reduced, or the least amount of oxygens. Okay, also, all hydrogens. Our oxidation reactions are increasing the number of oxygen bonds, okay, or a decrease in the number of hydrogens. As we oxidize, what happens? We've lost all of our hydrogens and we've increased the oxygens. Does it work perfectly? No. So let's do a slight tweak to it. Instead of looking at oxygen, let's look at increasing or decreasing the amount of electronegative bonds. Okay, so here we've got a couple different examples that we could go through and take a look at. For that first reaction, what happened? We've added a bond to chlorine, which means we have increase the electronegative bond, so we've got an oxidation. But if that's true, we should have seen something else change. What's the other thing that changed? We lost a hydrogen, which is also oxidation. Both match up for an oxidation reaction for that first one. Okay. Next one, what happened? So we gained an electronegative bond, but we lost an electronegative bond. The net result? Nothing. We gained electronegative and lost an electronegative. Nothing happened, which means it's not a redox reaction. Okay. What about the hydrogen that's out there? That hydrogen's not attached to our starting carbon. We're focused on that carbon for determining where our chemistry occurs. Okay. Again, you should be able to go through and apply these. Again, I want to push a little bit further forward. I can go ahead and post these. Do you guys want answers for these? Take that as a no. Talk to me later if you want them. Reduction. We're going to get into our reagents really, really quickly here. Okay. What do we need to do this reaction? To reduce to an alcohol. What changed? So we broke the pi bond. We gained a hydrogen.
Gained a hydrogen on the oxygen,
We
but you also gained a hydrogen on the carbon.
gained 2 hydrogens. What we did in this reaction was we added H2 to our structure. There's a variety of ways that we can add H2 to pi bonds. We've seen a couple of them. You got the Lindlar's catalyst and all that with your alkenes. We haven't looked at that with our carbonyls. Okay, when it comes to carbonyls, we've got 3 primary sources we're looking at. Sodium borohydride, lithium aluminum hydride, and then just straight up hydrogen. Okay, that's our same one that we've seen with our alkenes and our alkynes. So H2 with platinum or palladium, just force hydrogen across the double bond. Okay? The 2 that are new to you are the sodium borohydride and the lithium aluminum hydride. Done at 55? Okay. I know I'm pushing this, but I want to get into some of this actual new chemistry. How do these work? So let's take a look at our sodium borohydride. Okay, what's happening with sodium borohydride? We got the reagent drawn out for us nicely there. We got the sodium ion, which means, at least for the sake of this question, we can ignore that. We have that BH4 minus. What's going to happen? Sodium borohydride, so if we're looking at this, we've got to, let's make sure I don't have anything else. Talk about that feature in a little bit. We're looking at the carbonyl and how it reacts with a carbonyl compound. All right? And as Thuy was just saying, we're looking at a nucleophile. Sodium borohydride supplies a nucleophile. What is that nucleophile? Very, very close, Carlos, but not quite. Hydride. It's supplying a hydride nucleophile, meaning we're giving H minus. Where's that H minus coming from? How does that work? Go back to the Lewis structure of your boron. Boron is happy with only 6 electrons around it. It doesn't want the full octet, which means it has that empty p orbital. What can I drop into that empty p orbital? A pair of electrons from my hydride. Right, so sodium borohydride temporarily stabilizes the hydride nucleophile long enough that we can actually use it as a reagent to reduce our carbonyls. It won't react with alkenes. Why not? In the carbonyl, do we have a clear positive electrophile? Yeah, why? The oxygen is much more electronegative. We have a clear electrophilic position in our carbon. Very partially positive. Right? our oxygen is very partially negative. And when we looked at it with our alkenes, yeah, we drew in partial charges, but we're looking at kind of a weak balance between those. The charge could really oscillate between both. In this case, we're looking at a very clear dipole structure. When we go through and drop in our sodium borohydride, it's going to align such that that hydride, with its lone pair of electrons, lines up in one case, and just for the sort of sake of drawing this, our BH3 aligns in the other. The boron lines up nicely with the lone pairs on the oxygen, and our hydride lines up nicely with the positive charge on our electrophile. What ends up happening is we take the electrons from our hydride, attack our electrophilic carbon. What's the problem with that? Too many bonds. So what happens? We break the weakest bond available to us, which is the pi bond. Those electrons go to our oxygen. And what we end up with is an O minus. One of the reasons why the sodium borohydride works nicely is that that boron can still sit next to that negative to temporarily stabilize it. Because the boron still has that empty p orbital that can satisfy those electrons. Are we at the alcohol yet? No. What else is added? If we look at the rest of the reagents added in our reaction, it's typically H2O or an alcohol. Sorry, I can't make up my mind how I want to draw it. That oxygen is now relatively what? Negative, which makes it nucleophilic. So it could attack the boron, but that's a relatively weak interaction. So what else could that oxygen do? Accept a hydrogen or attack a hydrogen, meaning it acts as a base. The result is that we end up with our alcohol as our product. Okay? What happens when we look at lithium aluminum hydride? Virtually the exact same thing. Okay, and I'll leave you guys to decide. How happy are you with the mechanism that's drawn up here? Do you guys want to see it again? I'm not saying right now, I'm saying on Wednesday. Okay, Wednesday we'll look at it again slightly. That slight change that we're going to do is we're going to switch it to lithium aluminum hydride, and I'm going to do the same thing with the lithium aluminum hydride. Why can I get away with that? Where's boron versus aluminum on the periodic table? Right on top of each other. Their electron configurations are identical. We get the exact same properties between our aluminum and our boron. There are some slight differences which we'll talk about, which you can already kind of see in that upper right-hand corner. Our lithium aluminum hydride is a lot more reactive and will react with all carbonyls. Our sodium borohydride, much less reactive, will react with ketones and aldehydes, but it won't touch other carbonyl-containing compounds. Okay? I'm going to stop.